One of the most beautiful yet intimidating bodies of the universe has to be the planet Saturn. With its large rings and large gaseous body, Saturn flies around the solar system and provides tremendous impact for the planets nearby. In Roman mythology, Saturn was known as the god of seed or sowing, and how appropriate would it be for Sega's next iteration of console to be named the Sega Saturn? Maybe this could be their growing seed to be a mainstay in the video game market. However, this wasn't the case, and the Saturn was a huge flop. After being released in North America in May 11th, 1995, and retailing for $399, the Saturn ended up selling 9.26 million units, which is a lot, but it never really took off in the United States, and before you know it, the life cycle was over. With the life cycle lasting between 1995 and 1998 in North America, the Saturn didn't have the lasting impact that Sega had expected, and why is that? It certainly stems from the idea that the Sega Saturn didn't have many games to operate with. I think you all know by now. The hardware was a tremendously challenging platform to learn, and software developers became frustrated, but some of them prided themselves on being able to develop for it. Here's the story behind the famous hardware. Hi everybody, I'm James from Zygal Studios, and today we're going to talk about why the Sega Saturn was so hard to develop for. I'll be honest, when I first looked at this hardware architecture, I got a little bit excited. There are very few times where I start to get that excited feeling when looking at a hardware architecture, but this is certainly one of them. The Sega Saturn had 2 main CPUs and then 8 individual processors. These all made up subsystems both for the audio, the CD-ROM, the video, and the control unit system that eventually made this system work together. This system is so complex it can make somebody's head spin. And in fact, I may even take out subsystems or specific pieces of the system to make videos in the future on it. But for right now, we're just going to look at the overall hardware architecture. Let's start with the 2 main CPUs. The 2 Hitachi SHU CPUs were running right around 28.6 MHz. Both of these were pretty much exactly identical, however, there were a few key differences. The design philosophy for this particular system was to use one of the SH2s as a master and the other one as a slave. So this allowed for the first one to actually send some commands to the second, but also allowed the slave to be driven directly from the peripherals extended to that as well. This allowed for some asynchronous operations. While they weren't traditionally parallel, it was pretty close. The biggest downside to this specific design of the master-slave is that both the master and slave SH2s share the same external bus. This means that all the traffic coming in for both requests on the slave from the peripheral and the master can potentially have issues communicating with one another because everything is queued up waiting for a response. If something on the bus goes out to lunch, well, you're pretty much stuck with waiting. And that's about it. These processors were a little bit different in the way they were designed. As far as the status quo goes, for video game processor design in the 90s, this was no different. Both of the SH2s had a custom 32-bit RISC chip, but the instructions happened to be 16 bits long. This would reduce the size of the program and would use a SIMD technique considering the instructions are fetched in 32 bits, so 2 instructions can be retrieved in one cycle. This was paired with a 5-stage pipeline. For those who don't know, a pipeline in computer architecture is the idea of splitting up the stages of an instruction inside of the processor itself into discrete parts that can be run in hardware in parallel. So this way you can load the instructions based on how many stages of the pipeline you have to operate at the same time just at different parts of the instruction along the way. In this case, the 5-stage pipeline means that 5 stages of each of the instructions can be lined up. So 5 instructions are lined up in the pipeline and executed on. The longer the pipeline though, the longer the stall. So this was something to take into account. A few other additions to this processor would be a multiplication unit, 2 32-bit internal buses, and with having 16-bit instructions, this means that you could potentially have 4 different instructions being shoved around on this bus at the same time, and 1 32-bit external bus. A 4 kilobyte cache was set up in each of the CPUs such that they could cache instructions accordingly. The processors also contained a division unit and DMA controller. The DMA most certainly needed to be used, especially with this master-slave configuration. With this processor package, there was also a coprocessor known as the Saturn control unit. The DMA controllers that were in the CPUs also existed inside of the Saturn control unit as well. It needed to arbitrate between multiple peripherals in order to make sure that there were no errors on reception from peripherals inside of internal memory. But this allowed the DMA controllers inside the CPU to contact the coprocessor so that the CPU could do other things rather than handle all the memory addressing. The Saturn control unit was able to contact every single peripheral directly, and with this DMA controller, you could address each individual piece such that the main CPUs didn't need to touch it. It could only issue requests to it. The second processor in the coprocessor package was the infamous DSP that Coding Secrets or Game Hut talked about before. We'll get into this into a later video. But not only was this DSP pretty complicated to program for, it was pretty awesome. So go check out his video if you want to learn more right now. I'll cover this in a future topic. General purpose memory was also available on the Saturn as well. In this case, it was just RAM. But the trouble here was that between the 2 megabytes of RAM that were available, the upper and lower portions had different access rate and latency time, so you had to make sure that if you were going to access the high branch, which was the fast access portion, you would have to prioritize that versus the low access. So really, it was more efficient to organize data inside of the higher RAM access block rather than the lower. The SCU also couldn't even access the lower portion of the RAM anyway, so basically you were stuck with 1 megabyte. Now that we have an idea of how the controls were set up and how the basic design philosophy was, let's talk about the different subsystems that brought all this together. The Saturn control unit had 3 buses connected to it: the system bus, the A bus, and the B bus. Along the B bus was the video hardware. So we'll start with the video subsystem. Let's give a little bit of a background in terms of the 3D processing. So previously, games would have to render 3D on the fly, meaning that they would have to individually calculate and draw every pixel onto the screen using either some type of specialized hardware or just a CPU. The Saturn actually used what's called a frame buffer, which is what's still used today. So essentially, GPU would use a frame buffer to store information about what to draw on screen, and upon the draw call, the frame buffer would be populated and sent to the hardware. This would mean that this 3D generation wouldn't have to be rendered on the fly, meaning the CPU would have to draw every pixel on the screen. The CPU would simply issue commands to the GPU, fill the buffer with the necessary information to draw on screen. After this is completed, the graphics hardware is computed the geometric mathematics, the video encoder would use the frame buffer to then display that signal on the screen. This means that more memory would be needed in order to implement this type of a design. So 512 kilobytes of video RAM for both of the display processors were available. This means that you would be able to have 2 frame buffers deep. There were 2 separate 256 kilobyte frame buffers that could potentially use up to 512 KB of video RAM. One of the display processors was connected to the frame buffers, whereas the other was connected to the RGB encoder. This means that generally speaking, the control unit would issue a command to the video display processor 1 that would store data in VRAM and the frame buffers, and then display processor 1 would contact display processor 2 to have the video encoded and displayed on the screen. It was an interesting design, and it seemed to work okay, but there was criticisms that maybe the Saturn should have used a more traditional rasterization instead of the specific design. But here's the confusing part. While the Sega Saturn had basically more raw power than the PS1, and in almost every measurable way was either just as good, if not better, with geometric calculations and GPU performance, the PlayStation 1 did so much better. And why was that? And it was simply just because the PlayStation 1's C library support and its simplified hardware architecture was much easier to come to grips for people who made games. So while the Saturn was not only more flexible and more powerful, the PS1 was more popular with developers because they could get games done quicker and they could figure it out faster. Also along the B-bus from the Saturn control unit was the audio subsystem. This audio system was a pretty big powerhouse. It had a custom design in order to send it to the hardware. It consisted of the Motorola 68000 CPU, which you may recognize from multiple consumer products including the Apple Macintosh and the Atari Jaguar. It also included 512 kilobytes of RAM, a sound DSP, and a DAC to send the audio to the output. The custom sound processor had a multifunction sound generator, 32-channel PCM, was able to do 44 1K or CD quality of audio. The DSP was also able to perform custom sound functions like reverb, and with all this power on board, you need that 512 kilobytes of RAM in order to store for all these transformations. This is a pretty simple and straightforward piece of the architecture, so we'll leave it at that. Along the A bus now, we have the CD-ROM system. The CD-ROM system consisted of 64 kilobytes of ROM, 512 kilobytes of RAM, another SH1 CPU to control all of this together, as well as an MPEG decompressor. This was an optional piece of the system, and the decompressor could be used in tandem with both the audio and video system. With these 3 subsystems working together, and the cartridge port available also on the A-bus, This is a bear of a system to look at, but we haven't even gotten to the system bus yet, which is next. On the system bus, we have our two SH2 CPUs with 2 megabytes of RAM, as discussed before, and there was even 512 kilobytes for a bootloader that would tell the Saturn where to go in memory. These were then connected to the controller ports with 32 kilobytes of SRAM as well. So essentially what you had is the CPUs controlling the Saturn control unit, which would then be able to contact every single subsystem. So using these two CPUs in a master-slave format, you could issue DMA calls through the Saturn control unit to any of the subsystems, whether it was the video, the audio, the CD-ROM, or the cartridge port. Inside of these subsystems, you were also able to program each individual processor, meaning that there was a ton of variation and a ton of customization that you could do. But this also meant that it was much more complex to get things where you wanted them to be. So now that we have a basic idea of the hardware, let's talk about some of the challenges that developers saw with especially the 3D aspect of this console. There was a big problem from game developers with the Sega Saturn. This was being able to get their games out on time. It was a fine line between programmers and developers being able to master the hardware and make a shippable and playable, enjoyable game. So the games tend to range in quality as far as you can see now. One of the most challenging problems and fundamental problems in 3D graphics is figuring out, when you're in a camera perspective, what object is in front of the other. So if you're looking at an object and you're trying to determine in space where to draw, which object should go in front of the other. This specific problem has a solution called occlusion culling and is pretty well known now. And occlusion culling have numerous ways of being implemented. One of the most common methods that was used later on in hardware was something called Z buffering. During the rasterization, the Z value of each pixel is checked against the existing depth value. If the current pixel is behind the Z buffer, the pixel is rejected. So this means that the object that's behind the object that's in front won't get rendered, at least that part of it anyway. It checks to see if there's any overlapping pixels, and eventually, upon rasterization, those pixels will be rejected. You can also use a painter algorithm, binary space partitioning, ray tracing, coverage buffers versus a surface buffer, and the list goes on. While the N64 used Z buffering, and had hardware to do such things from Silicon Graphics, the Sega Saturn didn't have any specific way of determining which objects were in front of the other. In hardware, that is. The Sega graphics library did offer a Z-sort or painter's algorithm, which performed polygon sorting, but this was only a partial solution in my mind because hardware should be handling this task. That is exactly the purpose you have a separate graphics hardware from your CPU, in order so that they can offload these types of tasks. The biggest problem with this being implemented in software and not on the rasterization portion of it, like I mentioned before with the Z buffering, is that in the Z-sort, the Z value that's used to determine which should be drawn over the other is approximated. This means that there's error when displaying it on screen and when it's being calculated. So stretching and tearing can occur pretty easily. This actually caused most developers to completely avoid the Sega graphics library to begin with and just implement their own solution for their own game. So this was a tremendous burden to lift as a developer. Not only do you have tight timelines and complex hardware to learn, but the graphics libraries that are applied don't really give you the best options for rendering games, especially for the types of games that people wanted in 3D. This chose most developers to stick with either a 2D representation of 3D, or just typical side-scroller games that just use textures instead of polygons. Between that complex video subsystem that required a lot of custom code on it, the audio subsystem that required a lot of custom code on its DSP, the control unit, which handled a lot of 3D transformations through its very complex DSP, the two CPUs, the bootloader, and the CD-ROM subsystem being all controlled by this master-slave system, this was something of a monumental task to get games out on time and of high quality. And pats on the back and cheers all around to all the developers that were able to make such wonderful games for this system. It's one of the highest revered consoles in the collector market from Sega, and it has a pretty good cult following these days. With that being said, I think that this architecture is a work of art. You don't see video game architectures this crazily designed anymore. As a computer architecture nerd, it gets my blood pumping a little bit. But I hope you all appreciate the developers of both the hardware architecture and the games on the Sega Saturn now. And I really hope you enjoyed this video. Before I go today, I just want to give a collective thank you to the small community that's growing on my channel and is looking forward to these hardware architecture reviews of previous game consoles. Thank you so much for all the support and the love. I appreciate it. If you could comment, like, and subscribe, and share with the surrounding communities, I would be highly appreciative. And I have one last thing to ask of you guys. If you could leave in the comments an idea for video game hardware architecture videos, or just how video games work in general, please do so in the comments. I would love to make a video about it. I want to hear from you guys of what you want to learn about. And don't worry, I'm going to continue to make these videos. I would also like to give recognition to Nalak, the musical artist behind the music of the videos on this channel. If you could, give him a follow on SoundCloud and YouTube, which is listed in the description below. His music fits the mood perfectly for classic game discussions. Thank you all again, and this is James from Zygal Studios, signing off.